And what is really happening? When we do an adjustment or when we do a grinding or do something like this, initially for a tempered body, that is residual stress, it's very hard to initiate and grow those cracks. But subsurface, if there is tension, these cracks get into that and then it starts to run away and rapidly grow through the system. Now what do you guys got? Here you've got a cross-section, or here's a cross-section of a crown. Typically you would have the zirconia or coating material here, then you'd have a thick layer of porcelain. Where do you normally do adjustments? Somewhere here. And then this is able to then generate a crack into this tensile surface region in here, and with time that crack can grow completely and break off that cusp region. One final area to talk about this adjustment process. Again, you have selection of materials. This is the student Chi Chang, who was a guy at Dunedin doing his declin dent and prosthodontics, and he was interested in, well, what type of damage do I do when I adjust these crowns and these porcelains? And so he chose these 4 different materials: Velux, Velan Alux, which is for porcelain for alumina; Velan Xerox, for porcelain for zirconia; IPS Empress, which is for zirconia; and IPS Empress Aesthetic, which is a classic metallic type of porcelain. Here are the mechanical properties of these systems. Fracture toughness. Notice the fracture toughness of this porcelain is much higher. And he used 3 different burrs. And he mounted these on a traditional type of turbine systems that were used, typically 300,000 RPM. He ran it across. It had water cooling happening all of the time, just as you would in a clinical situation. And he used these 3 different burrs. What did he see? Here was the change of strength of these materials. This was the material, the Alux material for the alumina. Here was the strength initially. Here was the strength for the coarse burr. You can see that there's more than a 50% reduction in strength. In the finer burrs, he only got 10 to 20% reduction in strength. On the other hand, if we went up to this material, which is the material that was the aesthetic material, which was used for metal, virtually less than a 20% reduction. Why is that situation? This is the material that's got a lot of lucite in it. This is going to have much higher toughness because the crack's interacting with that system. These materials are virtually completely glass-like, so that once a crack is in that system, it rapidly grows. But what caused the damage? When he went to the SEM and looked at these samples, so here is the cut area across that surface, he saw these crack patterns. You see these crack patterns that are there. These crack patterns are thermal shock cracks. And so what is happening? In the trace of dragging the burr across the surface, you get very high temperatures generated because of the cutting of the porcelain. But because the turbine is running at so high velocity, it doesn't enable the water to get underneath the turbine to cool, underneath the cutting. And so as soon as the burr moves away from the area it's been cutting, the water can now quickly quench that adjacent area, and that causes this cracking pattern that causes the reduction in the strength of that material. So, how can we solve the chipping problem? Basically what we have to do is that we have to cool this material such that between the softening temperature and the glass transition temperature, we slow down the cooling rate. Because if we slow down the cooling rate, there will be limited difference in temperature between the inside and the outside of the porcelain. Once we're below the glass transition temperature, then we can increase the cooling rate again. But the critical region is between the glass transition temperature and the softening temperature. And this is my message to companies, and I visit companies regularly, and I tell the Vitas and the Ivoclars and the Estes and other ones that will listen to me, this is what they should do. They should, on their bottles, they should identify the glass transition temperature and the softening temperature. Recommend slower cooling rates, particularly for above between the TS and the TG, more critical, the thicker the crown is, the more critical is the cooling rate, the more critical that you have to slow. And they should increase the toughness of their porcelains. Why did the Noritake material not fracture? Well, it had lots of lucite in it, and it had much, much higher toughness. So it was much more fracture toughness resistant than some of these glass, very highly translucent materials and transparent materials. The role of the clinicians and technicians. Ask your technician to slow down the cooling rate, particularly for zirconia. And if you don't know the TG, or if you don't know the TS, then from about 150 to 200 Cs above the TG, you should slow down, particularly for thicker systems. The critical process is the final glaze. The final glaze cycle is the one that resets the stress structure in your system. So that is the one that you really have to slow down the cooling. Intermediate ones are not so important because you're going to heat up again, you're going to reduce the stresses and relax the stresses, but it is the final glaze firing one that is the most critical. Be very careful with your adjustments. You really need to do this with as fine as a burr as possible and preferably polish very substantially afterwards to remove the problems associated with it. But none of you like to do it. It takes time. And time's money. Alright, well I think I'd better stop at this point. This is my general conclusions. I'm thinking that chipping is a major problem, but it is relatively easily solved, provided that the technicians and companies will acknowledge the cause of that system. It's only really a problem in zirconia-based system because of the poor thermal conductivity. That does not mean it does not happen in other materials. If you have poor design, etc., you can still get chipping. But the preponderance or likelihood of chipping is much greater with zirconia. This is due to the tempering stresses in that system. It's also assisted, and I didn't talk too much about this, because of the high coefficient of thermal expansion. The higher the CTE is, then the greater the stress that develops. Pressed porcelains have the same problem as traditional systems, so really slow down the cooling rate, particularly for thicker systems. Thank you very much for your attention. Thank you. I must thank Shema and for all their support and help during the course of my stay here. I'm grateful to the head of department, your dean, and colleagues for the opportunity to visit here, and I very, very much enjoyed my stay in Egypt so far, and Mansoura in particular. Thank you very much.